suppose the capital K, or K is the number of regressors, okay, usually 10 or 20, and it's 10, usually larger than 20, okay, and beta K is of course the coefficient of the kth regressor, xk. Sk is coefficient, of course, and here is P, okay. Before then, let's consider here gamma K first, okay. Gamma K is on indicator function, okay. So if sk is important, sk is an important regressor, that means the beta K is non-zero, okay. Then gamma K is 0, gamma K is 1. And if sk is unimportant, okay, if sk is unimportant, in that case, gamma K should be very close to 0, right? So then gamma K has the value of 0, okay, 0, okay, and then this is the P is the this P is probability that each regressor is important, or this is also the prior probability that gamma K is equal to 1, okay, okay. So then to understand this model, we have to understand any model in terms of what? In terms of data generating process. Okay. So here P is assumed to be 0.5. Okay, 0.5. So then with 50% probability, each regressor is important. Okay. So then in the first step, gamma K is generated with this probability, okay? With probability of P, the gamma K is 1. And with the probability of 1 minus P, and gamma K is 0, okay? So then the importance of the kth regressor, which is just Sk, the importance of Sk is determined by gamma K, okay? So then the gamma K is just randomly generated from this Bernoulli distribution. Okay. So that once gamma K is determined, then beta K is generated from this normal distribution. And this is similar. This is very similar to the standard regression. But the difference is that is prior variance. Prior mean is 0, which is same as before, right? And then now prior variance is just a linear combination of two values, b1 and b0, okay? And basically b0 is very small number, it close to 0. But b1 is very large. b1 is quite large. This is quite far from 0, okay? So then if gamma K equals 1, which means the kth regressor is important, then gamma K equals 1, then prior variance of beta K is 1 times b1, which is just b1, plus 1 minus gamma K. Gamma K is 1, so then this term is 0, right? So that if gamma K equals 1, then prior variance of beta K is b1. In contrast, if gamma K is 0, then the prior variance of beta K is b0. Okay, so that if suppose that the gamma K is 0, then beta K is assumed to be generated from this normal distribution. Mean is 0 and variance is b0, and b0 is very small number. So then that means what? Beta K must be what? Beta K must be very close to 0, right? If gamma K equals 1, then the prior variance of beta K is b1. So then beta K can be taken any value. It could be much larger or smaller than 0, or even it can be close to 0, whatever. And then okay, then that's it. Okay, that's it. Right. So then right? Okay, then right, and then once beta k is generated, then we have also the sigma square is generated from this inverse gamma distribution. Once we have the uh, once we have the beta and sigma square, then y is generated from this just normal distribution. The mean is x beta, and the beta covariance matrix is sigma square times the identity matrix. And this is exactly the same as before, right? So then the only difference between this beta abstraction and the standard the regression is the prior distribution for beta, and this particular prior distribution of beta is called spike and slap prior. Okay, again, here is the intuition. Okay, so again, so beta k can take two kind of the price distributions depending on the value of gamma k. Okay, if gamma k equals one, if gamma k equals one, so then its price distribution is this normal 0 b1, and b1 is right. So then so price distribution is quite flat or quite diffusive. Okay, this is quite spread. However, if gamma k equals 0, then the price distribution is normal 0 b0, and b0 is very sharp. It's very sharp at 0. Okay, so then beta k should take the value around 0 or very close to 0. Okay, so then in such case the kth regressor is regarded as an unimportant or irrelevant regressor, and then this can be excluded in forecasting or the fitting the um, dependent variable. Okay, again, so then this is mother. Okay, P is given. P is in this example P is the hyperparameter. Okay, P is given. And in this case P is given at 0.5. Okay, gamma K is generated first from this Bernoulli distribution. Gamma K is generated. Gamma K is generated for each K. Okay, for each K. So then for each K, then gamma K is generated, and given gamma k and beta k is generated from this normal distribution, depending on the value of gamma k. Okay, so then by repeating these steps, we have capital K betas, right? Okay, right. And sigma square is same as before, and then given beta and sigma squares, the y is generated from this normal distribution. Okay, so now we are estimating this model. Okay. In the standard regression, there are two parameters to be estimated, right? Beta and sigma squared. Now we have the additional parameters, the gamma. Okay, and gamma in this capital gamma, they are capital K gammas. Okay, okay. So then our objective our objective is to simulate or generate the posterior distribution of beta, sigma square, and gamma. Okay, so then this is the likelihood, and these parts are the prior. Okay, prior. Okay, and the prior of beta, of course, depends on gamma. Okay, okay. So then, and then its small gamma k are mutually independent a priori. Of course, beta k's are also the independent, mutually independent, given gamma k. Okay? So then we now have three blocks. Previously we had two blocks, beta and sigma square, and then now we have one more block for gamma. Okay. Then let's begin with beta sampling. Okay, beta sampling. Okay, so this is the prior variance of beta. Previously it was B0, capital B0. Now this is V beta. Okay, and then prior variance of beta depends on what? Depends on gamma. Okay, so then in uh, some regression coefficients are um, close to zero, or the others are non-zero, or the some regressors are important and the others are unimportant, right? Depending on value of the gammas, right? So then, so gamma is a vector of the capital gamma is a vector of small gammas. Okay, so then this is k by one. Okay, this is 1 minus k by 1. This is a k by 1. This is k by 1. So then this vector is what? Vector of what? Vector of B0 and B1. Okay, B0 and B1, depending on the value of small gamma k, right? And then this die out. So this is now this is k by k matrix. This is k by k matrix. Okay, right? And then that's B0 is now B0 is replaced by V beta. That's it. And and there's nothing else. Okay. The only difference is just B0, capital B0 is replaced by V beta, and the others are the same as before. Okay. Okay. So this is the uh, this is the mean of the full condition distribution, and this is the variance covariance of the full condition distribution. The notation is a bit different. Previously, it was beta 1 and B1. Now, I changed the notation. Now, this is beta bar and capital B bar. Okay, but the formula are the same. But this may look a bit different because the prior mean is 0, beta 0, and prior mean is 0. So that's why it looks simpler. Yes. All right. Okay. Now we are moving to sigma square sampling. Okay. And there's nothing to explain. This is exact same as before. And then please note that in sampling sigma square and gamma k has nothing to do with it. Okay. Gamma k or the gamma is not used here. Okay.